Welcome back, everyone. I am absolutely thrilled to have you here today. Let's just jump right into it, shall we? Today, we're taking a really fascinating journey into the invisible architecture that runs our modern world. We're going to decode the OSI model, but specifically, we're zooming in on its incredibly powerful third layer, the network layer. Whether you're studying for your CCNA, maybe you're diving into cybersecurity, or you're a developer who just wants to truly understand how the internet actually functions under the hood, you are in the exact right place.
I want you to think about this for a second. When you type a simple hello in a WhatsApp message to a friend halfway across the globe, that message doesn't just magically teleport directly to their phone, right? So how exactly does your data find its way across the massive, totally chaotic web of the internet? What gets chopped into tiny pieces, addressed, converted into electrical signals, and navigated through a literal maze of global networks before being perfectly reassembled on their screen. And the system that makes sense of all this chaos? That's exactly what we're unpacking today.
Okay, let's look at the big picture first. The Open Systems Interconnection, or OSI model, is our standard 7-layer reference guide for how different devices communicate globally. Data travels from the application layer up at the top, which is where you interact with it, all the way down to the physical layer at the bottom, where it becomes mere bits of ones and zeros traveling over a physical cable or a Wi-Fi signal. Now, as it moves down, it goes through a process called encapsulation. Basically, each layer adds its own specific instructions. It's kind of like putting a letter into envelopes within envelopes within envelopes.
All right, here is our roadmap for this explainer. First, the OSI Reference Model. Second, inside the network layer. Third, IP addressing and subnets. Fourth, routers and path routing. Fifth, essential network protocols. And finally, number 6, real-world network troubleshooting.
Starting off with Section 1, the OSI Reference Model.
So, a classic trick to remember all 7 layers from top to bottom is this awesome mnemonic. All people seem to need data processing: application, presentation, session, transport, network, data link, and physical. Pretty handy, right? Today, we are focusing entirely on that need part, the glorious network layer.
Moving right along to Section 2, inside the network layer.
The absolutely crucial point here is understanding exactly what this layer does. The network layer is the third OSI layer. It takes data segments from the transport layer right above it, packages them into what we call packets, and is wholly responsible for logical addressing and routing those packets between entirely different networks. Think of it this way. If the physical layer is the asphalt road, the network layer is the postal courier, meticulously deciding the fastest, most efficient route to deliver your cargo from one city to another.
Now, this is a distinction that trips up a lot of people, so pay attention. The data link layer, that's layer 2, uses MAC addresses and switches to move data within the same local network. But the network layer, layer 3, uses IP addresses and routers to move data across different networks. An easy real-world analogy for you. The IP address is the building's street address. It gets you to the right location in the world. The MAC address, on the other hand, is the specific apartment number on the door once you're actually inside that building.
Let's dive into Section 3, IP addressing and subnets.
Every device on the internet needs a unique identifier, an IP address, and there are 2 versions in use today. IPv4 is a 32-bit system, which looks like 4 numbers separated by dots, like 192.168.1.1. The problem? 32 bits only gives us about 4.3 billion addresses. With smartphones, smart TVs, and IoT devices, we literally ran out of space. Enter IPv6. It's a 128-bit system, providing an unfathomably massive address space. We're talking more than enough for every single grain of sand on Earth to have its own IP address. This evolution was absolutely critical to keep the internet growing.
But before IPv6 took over completely, engineers came up with a truly brilliant band-aid for the IPv4 shortage, NAT, or Network Address Translation. Think about your home right now. You probably have a laptop, a phone, a tablet, maybe a smart TV. Inside your house, they all have private IP addresses grouped under a local subnet. But when they go out to the internet, your home router uses NAT to translate all those private addresses into just one single public IP address. It's an incredible space saver.
And how does that traffic actually flow? Well, there are 4 main ways a packet can be addressed. Unicast is a one-to-one conversation, like you loading a web page. Broadcast is one-to-all on a local network, kind of like shouting to everyone in the room. Multicast is one-to-many, sending data only to a specific group, which is exactly how live IPTV streaming works so efficiently. Finally, Anycast routes data to the absolute nearest available server, which is a technique heavily used by content delivery networks to make sure websites load blazing fast wherever you are in the world.
All right, Section 4, Routers and Path Routing.
Okay, let's step through the actual logic of a packet's journey. Step 1, your device creates the packet. Step 2, because the destination is outside your local network, something your device calculates instantly using its subnet mask and CIDR notation, it sends the packet directly to the default gateway, which is usually your router. Step 3, the router receives the packet, opens it up, looks at the destination IP, and checks its internal routing table to figure out the absolute best path forward. Dynamic routing protocols like OSPF or the backbone protocol of the internet, BGP, help routers constantly and automatically learn the fastest paths. And then step 4, it forwards the packet to the next router and the next until it finally hits the target.
Now there is a tiny detail here that literally saves the internet from collapsing. TTL, or time to live. Imagine a packet gets lost between poorly configured routers, just bouncing back and forth forever. No way, right? If millions of packets did this, the entire internet would crash. So, to prevent this routing loop, every IP packet has a TTL counter. Every time a router processes a packet, it decreases that counter by 1. If the counter hits 0, the router just goes ahead and deletes the packet. It's a really elegant, self-cleaning mechanism for the web.
Section 5. Essential Network Protocols.
The crucial point here is that Layer 3 isn't just about moving data. It's also about network health. That's where ICMP comes in. The Internet Control Message Protocol doesn't carry user data like your emails or photos. Instead, it carries operational information and error messages. So if a router is overwhelmed or a destination is unreachable, ICMP is the protocol that sends the warning message right back to the sender.
And this theory becomes practical reality every single day. IT professionals use ICMP through 2 command line tools you might have actually used yourself. Ping sends an ICMP echo request to a destination to simply ask, "Hey, are you there?" If it replies, you know the connection works. Traceroute is even cooler. It intentionally manipulates that TTL counter we just talked about to map out every single router hop your packet takes to reach its destination. For sure, it's the ultimate diagnostic tool.
Before we leave the protocols, we absolutely have to mention ARP, the Address Resolution Protocol. Remember how we said IP addresses are for the network and MAC addresses are for the local hardware? Well, when a router needs to finally deliver the packet to the exact physical device on a local network, it knows the IP address, but it still needs the MAC address. ARP is the essential translator that broadcasts a message asking, "Hey, whoever has this IP address, please tell me your MAC address." It seamlessly bridges Layer 3 and Layer 2.
And finally, Section 6, Real-World Network Troubleshooting. When a user complains, "Hey, I can't reach the website," you don't just randomly guess what's wrong. You use the OSI model from the bottom up. First, Layer 1, physical. Is the cable actually plugged in? Is the Wi-Fi even on? Layer 2, data link. Is the local switch functioning? Layer 3, network. Do we have a valid IP address, or is there an IP conflict? Layer 4, transport. Is a firewall blocking the TCP port? And finally, up to Layer 7, application. Is the DNS service actually resolving the domain name? This kind of structured thinking is exactly what separates the amateurs from the pros.
As we wrap up this explainer, I want to leave you with this thought. The network layer organizes the absolute chaos of billions of data packets flying around the globe every single second, routing them with pinpoint accuracy, completely invisibly to you and me. It really makes you wonder, what other incredible, invisible systems are quietly keeping our modern digital world running while we sleep? Keep exploring, keep questioning, and keep learning. Thank you so much for joining me today, and I'll see you in the next explainer.